This is it. Hopefully this is the one. Okay, so welcome everybody. So this is week 11, day 1, and now we are finally, hopefully, getting it running. And if not, then we're sticking with it. It's gonna go on YouTube. So okay, let's go ahead and jump right in. Oh, that's not what I wanted to do. That's weird. Here we go. Okay, sorry, we teleported to the Death Star for a second there. Okay, so okay, so we're gonna continue talking about hashing, like mostly just finish some stuff, and then from there, I also wanted to talk about the pros and cons of the different collision resolutions. So I'll put that in here. Pro cons of each. And then I'm gonna talk to you about that worksheet, and then from there we are going to, I think, oh well, we'll talk about crypto hash, I suppose, crypto hashing, which is a little bit about like the homework, which you guys are already working on, and then from there, I think we're gonna talk about tries today because I just get something out of the way, and then we will introduce graphs if we get there. If not, I'd rather end class. If it's like close to end of class, I'd rather end the class early and then just spend a longer class talking about graphs because that subject is like contained in one big video. So I think that's the better way to handle that. Okay, so the first thing though, I do want to talk about the worksheet because it's due tonight. So let me go ahead and switch that over here. So let me turn off that. Okay. So, I'm gonna just go ahead and pop it open here. So, by the way, I posted a link on Canvas which has references for hashing, which I recommend that you check out. In fact, I'm gonna open up this one, and this one, and this one for later. But that's all the ones that I've been talking about last week. Furthermore, you guys had your test run for the test. My feed keeps dying saying your browser encountered an error decoding the video. That's more of your error. So just try a different browser and try refreshing. Yes. Use debugger. Okay. And so oh, interesting. But yeah, so if you guys went ahead and took this thing, which you better have, I can see here that everybody voted. Yeah, well, actually, I lie. Not everybody. One person voted no answer. I don't know who that is. I'm going to go check and yell at them and see why they voted that. But otherwise, the test is set for April 17th, 2020, between 12 and 12, basically. So I did it 11:59 to 11:59 so that people don't get confused with the date, the due date. But it's basically on the 17th, from midday to the end of the day. And is it laggy still? Yeah, I can see a little bit laggy. I'm gonna close the preview again just because we can see it's better. Oh, by the way, we have 62 viewers. That's the most we've had. That's pretty sad because the stream has been kind of iffy today. But yeah, so the test, all 62 of you, you know, there's 92 of you, but 62 are here right now. The test will happen on the 17th, and as you saw, there was an example of what you will see, which is basically you give a question and then you upload the question's answer. And I'd rather split them into each question individually because if I just make one big upload, I think it'll be harder for the TAs to grade. Oh, snap. My kilobits per second is at 29. Yeah, it's definitely frozen right now. But at least the video will be good. So, okay, I think it's green now. So yes, it's fighting right now. It's like it's fighting for its life for the upload. So just bear with it. If I would try refreshing if it's out of sync, to be honest. Okay, I think it's stable again. Cool. I know it's getting worse, guys. That's sad. I can't. There's not much I can do out there. Cox came, they left. Nothing good happened. And so yeah, I'm paying for Gigablast, but still got that horrible internet. Yeah, some of you might have to wait for the video. So I'm sorry about that. That's just completely out of my hands. So okay, And so as you saw, you get a picture of some sort. That's why I put these pictures as a test. You might see a tree as a picture, and then you have to do the traversal on that tree and so on. Okay? So yeah, the internet has corona indeed. Okay. When it says text answers, you want it typed or handwritten. So if any question most of the questions will be file upload questions. So you can write, draw, whatever you want to do to answer the question. In the case that the question does not allow you to do file upload, it means it's a text answer. And those will be ones where I'm confident that you don't need internet for you don't need internet. See, that's because I saw the F in the chat for the internet. You don't need a drawing for those. Okay. All right. So anyone have any quick questions about it? Like not about what's going to be in the test, but how the test is going to run. And yes, I do have 13% packet loss. Last I checked. So yeah, anybody have any questions on how the test will run? We'll go over the test next week. We'll have a review day. We'll have 2 review days technically, but I just want to know the implementation of the test if anybody has any questions. Will there be another test day during the lecture for like test 1? No, they will all be during the same one. That's why you got that question, and that's why everybody answered that they are available within that time period. And everybody voted yes. There was one person that voted no answer, but I said that they should contact me. And so far, I have had 2 people contact me, and that's why I extended the time to 12 hours. At this point, nobody else has contacted me, and you were giving enough notice, so that's the time it's happening. Oh, I meant a review of the test beforehand. Will there be another test day during lecture? Like, well, I don't know what you mean. We will have a review day, if that's what you're saying. Like, we'll have one review stream where you just ask questions. And once I have the test done, I'll also tell you some subjects of the questions. Oh, by the way, I've decided that because the test is open notes, there will only be 1 extra credit question, and it will be a programming question. And it will be separate from the test, actually. It'll be a completely different upload section that will be available basically for it'll be like the test. You'll see like 2 tests basically. One of them will be the regular test, and one will be the extra credit question test. And that's because when you finish the test, I want you to submit that, and then you can start the extra credit, and that way you don't get so busy with the test and something happens and you disconnect. No, I just get the test done, and when you have that extra time, you can apply for the extra credit. In fact, because it's separate, even though you will have the more likely the 3 hours for the test, you will still get you'll still get that extra time for the extra credit, which I'll give you like an hour or something, or half an hour. I don't know. I'll see. I am gonna make the TAs take the test next week. Maybe this week actually. Probably this week, and then assuming that they take an hour and 15, which is what I'm aiming for, then I'll multiply that times 2, and that's your time, which is, I think, that 3 hour period is going to be about then. Okay, so let's see. We got a bunch of questions here. So is it confirmed that if we have a coding question? Oh, I mentioned that. Yes, it will be the extra credit question. Turn in CPP file. Yes, it will be a turn in CPP file. If you're getting, okay, that's people troubleshooting. How many questions will there be? We'll talk about that during review because I don't have the test done yet, but you can expect around 20 questions. Is the extra credit super hard, doable by most? It'll be an extension of one of the assignments, which means you better have them ready to go, because I literally was thinking about that when I was showering this morning. So I have the question now for the extra credit. Viewers are leaving. Yeah, well, it's kind of crappy connection, so not surprised that they're leaving. So can we only want to smash for extra credit? No, extra credit for the test is basically how it is, and there is no skeleton code. Your assignment, any of the assignments that we deal with subjects of the test, are going to be your skeleton code for implementing what will be the bonus question. Yeah, I think it's stabilizing a little bit. I think lowering the bitrate is kind of helping. I can even lower it further if it's not too blurry. Okay. Finally, I went ahead and upload. So the worksheet, where's the worksheet at? Yeah, worksheet that is due tonight at, yeah, tonight in 12 hours essentially. 11 hours and change. It's blurry, but it's doable. Yeah. Okay. So let me pop open the worksheet for a second to clarify a couple of things. in case hopefully you did them and now you have time to change it. So these are the kind of questions that you'll see in the test, except you'll be uploading the answers instead of, I mean, as you are for the worksheet in a way. You'll get a picture of a tree, and then you'll do things like traversals. You will get conceptual questions, and you'll explain it with pictures and text, and so on. For this one, some confusion about that. You have to take those 2 traversals and use that algorithm that I taught you to generate the tree. For this one, you have to insert them. Anytime that you see just something like this and I tell you insert into a tree, you have to go from left to right, starting one at a time. And then here, after you insert them, you have to rotate if necessary. The heap one, however, is the exception to that. The heap one, you have to start with the built-in, like you did in assignment 9, I think it was. With the heap assignment, you start with the array already pre-built, and then you have to heapify the array, which is a different algorithm than inserting one at a time. So you will heapify it then, and then you will use the insert algorithm there. The difference there, as one of your students refreshed me on, which is the Triforce thing. So just to make sure you guys are clear on this, heapify is taking existing array. I'll get to your guys' questions in a second. And converting to heap. So you consider the array to be a level order traversal, how it's set up, and then from there you do that Triforce thing where you heapify that, and then you heapify that. But when you heapify that, it's possible that like maybe this guy and this guy swap, so you got to come back down and reheapify that part. So that's the whole the Triforce thing, if you remember. And then insert is the one where, for example, you just insert one more node and then you have to bubble it up to where it has to go. Okay, so that's the insert algorithm. Okay, and then for the hashing one, you have to take these values from left to right again and insert them into the following using these. We'll refresh a little bit about the different addressings in a second, but for this one, you have to create a hash function that gets you that perfect hash. And yes, I will ask that in the test. Okay, so let's see, PTSD, number seven of the worksheet. Number 7. Wait, do you mean tomorrow? No, it is due tonight. All right, number 7 of the worksheet. Okay. So let's talk about number 7 then. As I said, provide an example of a combination of a hash table hash function that you could use to insert Q6 without a single collision. So, okay, if you're hardcore, then you will use the same table size and you will create a hash because it is possible to do it. You just have to find some math that you can apply to those numbers to make them all unique. Now, when I talk a little bit about crypto hashing, you'll see that the reason you're having such a hard time with that is because of something like the birthday paradox, which is that no matter what you do to things, there's still going to be things that collide when you have such a limited amount of space where you're inserting. In the case of a birthday, the birthday paradox is that you got 365 or 66 possible days where you can have a birthday. And if you just ask 2 people in the room if they have the same birthday, it's a very, very low chance that they do. However, if you throw in about 23 people in the room, there's a 50% chance that 2 of them have the same birthday. And you're like, 50% chance of just 23 people, but there's 365 or 66 days that it can happen. And it turns out that math shows us the way and how that's actually a thing. And that is why, well, that's as much as I'll say until I actually get to that topic. But anyway, so this is kind of why you're having such a hard time. So here's the thing. If you're too weak, you can't handle the heat of making that function, then for a minimal amount of reduction in your respect, you'll be ashamed. You can make a bigger hash table and then another hash function for it. But I will be like, look down, because in the test you will have to do that. But yeah, probability theory. So okay, so yes, I didn't want to tell you guys yesterday because I really wanted you guys to try to respect basically how hard it is to come up with a hash function that's good. That's the purpose of that question, for you to realize like, okay, this is not just an easy thing. Yes, it only took 5 hours, as it should, you have to respect that question. So I'm glad, because now when people say, oh yeah, you know, hash tables are great. Oh, one time you just slap a hash function, you know, put some modulus in there, maybe multiply things, add them, and you can call it a day. Not really. Hashing can be quite tricky. And the cool thing is it can take you 15 to 25 minutes if you happen to guess the right hash function the first time. So, yeah. All right. So, get everything else done before you do that, though. So, yes. Okay. And then that's an easy question, question 8. Again, example. This is a refresher. Remember, if this is not asking you to explain. This just wants something. I can't tell you more because I tell you the answer. It just wants something really tiny. In fact, character-wise, it's like 6 or 7 characters, right? Let's see. 2, 3, 4, 5, 6, 7. Yeah. 6 characters, I think. Depends on how you write it. But, yeah. So, in the test, if you get a question like that, that's all you write. Those 6 characters. You don't need to write a story of how that came to be. So, okay. Asterisk, asterisk, asterisk. Okay. All right. So I think that's enough of the busy work stuff. Let's go ahead and go back into the iPad now. Where's my mouse? Let's see what Discord people are saying. Yeah, you guys are having troubles. I think it's actually more stable now. By the way, my dog is literally sitting here, so maybe she'll cameo at the end. Okay. So, let's kind of refresh these because I kind of rushed that at the end of class. And I'd rather, well, these two, I'd rather touch a little bit more on that. So, are we not allowed to back to the questions? What do you mean by that? Are you saying you're not allowed to explain them? You can explain them all you want. However, it's time you're wasting and it's not needed. Oh, you're asking if you can go back to the questions. So I will allow you to be able to go around the questions so that I think you will see one question at a time, but you will be able to go back to them after you answer them within the time period that you're given for the test. No, I was referring to question 8 being only 6 characters for the answer. Question 7, yeah, I mean the hash function is not. You can't write it in 7 characters. I mean, maybe you get a really good one. You could. I don't know. Okay, so let me get this water. Yeah, imagine doing that. It might happen. Okay, so the only thing I want to refresh you on probing is that, you know, it's not cool. It's kind of nasty. But it is something that it's useful to know to understand collision resolution and ways that you can still keep the data within the same array and not have it grow with linked lists that just grow on forever and things like that. And when you have your function h of x and you have linear probing, what you're doing is you're creating a g of x that is basically taking the original h of x and adding +1 the first time. But the second time, you're taking that value you had before and you're doing that to it. You're taking the old value and adding 1 to it. And that works to explain how linear probing works. However, with quadratic, it's not as easy, because with quadratic, what you're doing is you're taking I, which is the ith collision, and then you're squaring that. And you can't really write that nicely into a function like this. So while I would say that linear probing is a special case of double hashing, quadratic probing is not really, because unless you were to make something like g of x is equal to h of x plus I squared, something like that, then that would work. And I mean the iteration or the collision. So the first collision, second collision, third collision. So if you want to do it like that, I suppose you could say that, but then you have 2 variables involved. Whereas normally this is taking the old value into that. So yeah. And the other thing, when you have your collisions, so say you have your your hash table here, and you have collision in spot 3. This is spot 3. The first time you're trying to check 3. The next time you're trying to do 3 plus I squared. So I being 1 in this case. 1 squared means check 4. So every time with quadratic probing, the first spot you're going to check after a collision is the next spot. So in that sense, it's like linear probing for the first collision. From there, this is the part where people sometimes mess it up. And I don't want you to mess this up in the worksheet or in the test. From there, the next part you're going to check is still 3 plus I squared, but I is now 2. So it's 3 plus 2 squared. So this is basically 3 plus 4, which is 7. So the next part that you're checking is 7. Okay? What people what people, hold on a second. Sorry. Yes, I did mute myself because I have my dad is visiting and he was making noise, so I wanted him to stop talking and to stop making noise. Yes, exactly, to get rid of the background noise. Sorry about that. My apologies. So yes, I didn't want to. Okay, so anyways. Okay, so what I was saying is when you get to the second collision, that shifting that's happening, so I squared, 2 squared, 3 square, 4 square, you're going from the original spot. You don't add it on. So here's the wrong way to do this. You're thinking, oh, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 16. And you're just like, okay, I'm going to go one spot there. So from like 3 to 4. And then from there, I'm going to go to spot 8 because it's 4 more. And then from there, I'm going to go to spot 8 plus 9, which is 17. That's not the way to do it. I mean, you could, look, that if you're doing double hashing and you want to do it that way, you can. But with quadratic probing, what's really happening is you're doing that shift from the original value. You don't just add on the squares. So you do the original index plus 1, and then the original index plus 4, and then the original index plus 9 from there, from the original index, not from the previous spot that you checked. Does that make sense? And yes, you can use ion double hashing, as I said that. So yes, and I know a lot of people kind of mess that up, but that's the purest way of doing quadratic hash probing, is doing it from that way. And a lot of people sometimes get that confused. And like I said, it's a perfectly valid way of hashing, but it's not the purest way of looking at quadratic probing. So with double hashing, which is the next thing I'm going to talk about, you can do whatever you want and any way you want. And so it could be just as easy as saying my g of x function is going to be the previous value. So the first time it's like, it's going to take h of x's value and maybe add plus 2 to it. And then the next time that you do that, it would be g of x. So that would be like g of x is equal to the old g of x plus 2, and so on, and you nest them. You could do anything with like addition, subtraction, multiplication, division, modulus if you wanted, although that's not going to get you too far. Any mathematical representation, but you're programmers. This doesn't have to just stick to math. You could put, this is a function. You could put an if statement with logic involved, like checking different bits, or checking the different spots in the number, or converting a number into something else, applying another function, the math function, hard coding values, like you always want 22 to go to some spot. And so that's an easy way to solve a question 8. Actually, you can, this is dumb, but you could literally hard code all values to go to specific spots. But I would say that's kind of not really taking advantage of the hashing the way that it should. You said you discourage this from quadratic probing, so the people are using the application. So as far as I know, when you're using a map or a dictionary in a programming language, it's usually using hash table with closed addressing, which is a separate chaining. It's usually, instead of using linked list, using an AVL tree. As I said before, that's better. I don't know if anybody ever really uses open addressing, like quadratic probing or that kind of thing. So better yet, that's why I wanted to complete talking about it. Let me really get into more detail, because I rushed it last time, on the pros and cons, so that if your pros really fit on a specific category, then I guess you would use open addressing. So okay, let's see. And it depends on your data. So yeah, that too. Okay, so here I have a piece of paper I'm gonna take out. Or actually I'll just bring over. And this is from Geeks for Geeks, on one of those links. And there's a pro and con on separate chaining versus open addressing. Again, separate chaining is the same as close addressing. I always get them all mixed up, but you guys won't. Lag. I got green, so it's all good. All right, so okay, so separate chaining is simpler to implement in terms of, or at least simpler to implement in terms of computation time than, oh, maybe I should wait a second and let the lag recover. I am seeing here that I have a clean upload. So try refreshing. Yeah, refresh. So because I have green light, so this tells me the bitrate, and right now it's green. So I don't think that that it's me this time. It might be your internet this time. Okay. Open addressing requires more computations because you have to recompute every time you collide. In linear probing, it's as simple as adding 1 to it. In quadratic probing, it's squaring a number, which I suppose in a way can be computationally expensive once you get to really big numbers. But you could hard code those numbers. You don't need to you don't need to recompute what I to the 10, I squared, 2 to the 10th power, 2 to the 11th power. That's always going to be 2 to the 10. It's never going to change that number. So you could ahead of time save those values into a array or something, and then just refer to them based on the collision. So that would be kind of like dynamic programming. That would be like in Fibonacci. Instead of recomputing every time, you save previously computed Fibonacci numbers so that you can use them again without recomputing them. We'll talk about dynamic programming at the end of the course. But ultimately, the computation time required for something like that is not as bad. However, once you get into something like double hashing, where that second hashing could take computation time, then that I suppose makes it a little bit harder. Next, in chaining, hash tables never fill up. We can always add more elements to chain. And by the way, I guess I'll repost it, but I am talking. This is all coming from Geeks for Geeks. On the the one that says set 3 open addressing. Yes, memoization. That's right. Memoization is in Python, and that is basically dynamic programming. I feel like I mentioned it in 302 in person, memoization, when we talked about I don't know. We talked about it one day, and I showed you guys. I'm 100% sure. It's the only time you've seen Python code in class. I think it was when we were talking about Fibonacci, actually. So yeah. But anyways. So, by the way, hello to that person. I don't like saying people's user ID on stream because I don't know if I want to get called out or something. But hello. All right. So, unless you guys are fine with that, chaining is, as I was saying, it never fills up. You can always add more. So you can add as much things as you want to your hash table in separate chaining, and it's okay because at the end of the linked list or AVL tree, so they can just keep filling it up forever. No problem there. The disadvantage with open addressing is that it can get full, and once it's full, you're screwed. And not just that, but with something like quadratic probing, it doesn't even have to get full before you can't even insert, right? As you guys probably saw in the worksheet. And so at that point, it's like we have space, but we can't insert. Too bad. So what do you have to do? You have to rehash. Rehash means you have to make the table bigger and then change your hash function so that it can take advantage of the table. However, technically, you don't have to change your hash function with open addressing, because if there's collisions, then it'll just keep going to the next spot. However, it's highly discouraged because you already have collisions in the first place. You might as well kind of change that a little bit. At least put a modulus at the end of the values, or change the modulus in there to take advantage of it. Whereas with separate chaining, you always have to change your hash function. Otherwise, you will never take advantage of the extra space because it'll just keep adding into the linked list. When we need to resize an array, by how much should we resize it? So the trick that somebody said, and I agree with, is you typically want to keep your hash tables of prime number of size. So then you just go to the next prime number, or double the number, or double the number, and then from there go to the next prime available, and so on. So it's strictly your choice based on data. Okay, so when do you use each mostly? Because that was a question that you guys were asking me, like, when do you want to use open addressing, if ever? So open addressing is used when the frequency and number of keys is known. So if you know that how much are how many values you're going to put in and how often you see certain values, then I suppose you could use that. Although I would say I would stick to chaining, because that's useful when you don't know how many keys you're going to have or how often they're going to be inserted or deleted, which is fine with me. I don't care. But there's that. The one real advantage of open addressing is that because everything is kept in the hash table itself and not in the linked list, then you can very easily access data in terms of cache performance, because you can load up the entire table in the cache, whereas anything with pointers is much trickier to load on cache because it's all over memory, and the 219 stuff, the computer is not going to be able to predict where the next data that it's accessing. This really jumps into 219 material, but to speed computers up, they like to predict what we're going to do. And if they know, if we're accessing an array, say we're just printing an array with a for loop, and the array is really big, you're printing a system class star destroyer array from assignment 2 or 3, whenever it was in a vector array. And so from there, if it just sees you that you're just in the for loop running, by the time you get to like the 20th element, it's caught on that all you're doing is printing up this array. So what it'll do is it'll preemptively try to load that array into as close as it can to the CPU so they can process the data and print it. And so, as I was saying the other day, you have RAM, or here, I can use pictures. You have your rig, like you guys have with the little anime thing or doll in there or something somebody had. So from there, you have in your rig your RAM modules, and then you have your CPU. And you'll notice that they're usually relatively close, sometimes annoyingly close, that it messes with the cooling system. Well, it turns out that there's even closer memory to the CPU called cache, and there's different layers of cache. And so when you're trying to process an instruction, and then of course you have even further away here, I guess no more weave stuff here, you have your CPUs. So, oh, my upload rate is bad. Okay, give it a second. Come on, it's getting a little better. Okay, it's better. So here we have it, the CPU, or sorry, the hard drive. If you want to load something directly from the hard drive, like you're trying to play a game, or actually you're trying to run sorting and it's stored on the hard drive, that is super slow. So what you do, you load it in RAM, but RAM is limited in size, but you try to load as much as you can. But it's still slow because data still has to travel, speed of light and everything, into the CPU. So what they did is they created these little tiny little memory modules of really fast memory here that are about like 4 megabytes that are called cache. And when you put data in there, it's much closer to use. So you ideally want to have memory that you're about to use here. So with a hash table or an array, as you're printing this and you're working through this and you see that this is going to come next, the computer predicts that, it will preemptively copy this into your cache. And then from there, it'll access it much faster. Whereas with anything with pointers, it copies the pointer, but it might be pointing to somewhere in memory up here that's not loaded in cache. So now it has to copy it over to the cache here and then send it to the CPU. So it's a much slower operation. So that's why arrays are a bit faster, because the computer can predict that. And so that, I suppose, is the biggest advantage of open addressing. And And in general, the advantage of anything that involves arrays and doesn't involve pointers, because pointers are unpredictable on where you're going to go next. Trying to print a linked list, it's all over memory, right? So it's very, very hard for the computer to predict where that is stored in memory. So, yeah. Okay, so you have a question. Or when we need to reset. Oh, well, I thought, yeah, you guys answered that already. You're good. What about Discord? When do the videos really up? Oh, by the way, yeah, the videos tend to go up the same day around 6 p.m. So I try to, as soon as the lecture ends, start the upload. It's like 11 gigabyte file. Gigablast should be able to handle it really fast, but of course I don't have that. So it takes about an hour to upload and then about 2 hours for YouTube to process. So that puts it around 4 or 5. And processing to get the HD version takes a little bit longer. So usually by 6 p.m. they're up. That's why I put the unlock time. So yes, just check my channel. Don't forget to like and subscribe. Okay. And we're on our way to Twitch affiliate right now, technically, because we have so many viewers. So that's cool. Okay. Open addressing provides better cache performance as everything's stored in the same table. Open addressing, a slot can be used even if an input does not map to it. Oh yeah, I suppose that's actually kind of a good thing. So if you have a separate chaining, you know, hash table, and everything is always hashing to these 3, you know, there's going to be cases where like spot's not used, but that's okay. You know, technically with probing that can happen too with something like quadratic probing. With linear probing though, you can guarantee that that's like you're really cheap with space, and you want to make sure you take advantage of all of it. So that comes into the next thing. Separate chaining can waste space, whereas open addressing does not if you're using linear. Quadratic though, it can turn out that you may waste space actually because things go squares and they never fit in other spots. I do want to point out that there is a thing known as load factor, which is something that you want to use and apply when you're dealing with open addressing, and that is when your hash table gets. Actually, you can use it too with separate chaining, but the idea is that as your array gets full, then you want to resize it before it gets too full, maybe more than 50 or 75%, because the fuller it gets, the higher the chance that you're gonna have a collision, and that's just math. And so before it gets to that point, that's when you just want to cut it off and be like, that's it. We're going to stop this inserting, make the table bigger, and avoid reinsertion. Now, of course, that's an expensive operation. Rehashing something is going to take potentially n time and being the size of the current list, because you got to copy all the elements out of the list and into a new one. And for each one, you have to insert it into your hash function, which is O of 1, but it's still n of them. So it's a slow operation. And hopefully, if your data is just coming fast and furious, then it's going to slow things down by n time. But if it's a real world application where you're slowly putting data in at intervals, once it gets to that load factor and there's a gap, that's when you're going to do your rehashing overnight. And also the next morning, it's all good to go with more space, less chance of collisions. So that's rehashing and load factor. And that's also on Geeks for Geeks if you want to read more about that. We have a question. Should there be a case when we use linked lists over ABL trees in close addressing? You should always use ABL trees in the real. I mean, like I'm saying, it's just mean to make you do that in like an assignment. Although I have done it before. I think last semester in 302, not last year in 302, because last semester in 302. It's not too bad. I mean, you get the algorithm set up. You just gotta hook them up together. But that's how most libraries are actually implemented. Hash libraries, like I was saying, they use separate chaining and they use ABLs or red blacks, but I do believe they use ABLs. Like if you Google how the Python library is implemented, I do believe that's how it's actually implemented. Of course, they got some really nasty, and by nasty I mean amazing hash functions to get things going, but they can't. Is there a reason someone use red black trees over ABL trees? I talked about it the other day, even though we haven't talked about red black trees, and we might at some point, but it's not part of the lecture. I only required to do one of them, and they'll cover both in analysis of algorithms, but red black trees, you can insert faster and there's less rotations. ABL trees is a little bit slower insertion because of all the rotations. It's still log n, but it's just in application, it's a little bit slower. However, retrieval is going to be much, much faster with an ABL because, again, they're all log n, but it's more balanced. Whereas ABLs are a little bit less balanced. It's still log n, but it's like on the higher end of log n, so retrieval will take a little bit longer. By the way, talking about insertion, no matter which method you use with separate chaining, you can insert things in O of 1 time. I suppose if there's a collision and you have an AVL set up, then it's log n time. So I guess that could be one tiny pro of using a linked list over an AVL. If you just want to guarantee that O of 1 time, you could use a linked list, because you can always insert in the linked list O of 1 time, right? You just dump it at the front or at the back with the tail pointer. With the AVLs, it does have to be log n. So I guess if you really were insistent of keeping that O of 1 time, you'd go with the linked list approach. You definitely will not get O of 1 time with open addressing if there's a collision, whereas with linked list you would. So there's that. With retrieval though, with separate chaining, it can take up to n time if you're using linked list, or log n time if you're using AVLs for the chains. Whereas with open addressing, you may have to work around the entire table, right, to find something. So that's going to always be O of n time, and that's not great. Okay, that's it for that. So that is the end of hashing. Any more questions on hashing? I'm out of water, so that sucks. Okay, well, I'll check again for questions. So how are we doing on viewers? I have it closed, so let me know how we're doing on viewers. Why is it called hashing? Because of the hash function. That's it. Now, why is it called hash function? That's a good question for Google. Why is it called hash function? Because of hash tables, I guess. Yeah, that's not a, but nope. I don't know. That's a great test question, yeah. Could you give a brief rundown of open addressing, linear probing, and all the other hash functions? I just did. I did. So linear probing is just you plus 1 every time you collide. Quadratic, you I squared. You go spot 1 just like linear, but from there you go to spot 4, and then spot 9, and so on. And then double hashing is you just create another hash function. And yes, linear probing is a type of open addressing. Okay. I lied though, we're not done with hashing. I said we're going to talk about cryptographic hash functions. So, okay. So in the assignment that you see, you're actually implementing the Rsa algorithm. And I don't want to talk too much about that specific implementation, because I think that that's a good way for you to learn it when you read that and you apply it. But it's very cool because it's a security thing. So more I want to talk about in general about using hashing for security, or cybersecurity as I like to use it. And so a cryptographic hash function, I'll read this to you. A cryptographic hash function is a special class of hash function which has various properties, making it ideal for cryptography. There are certain properties that a cryptographic hash function needs to have in order to be considered secure. So what is security? Well, that's what we kind of need to expand on. But first, let me tell you what these properties are, and then it'll make more sense. So what we're saying with hashing is I have some input in plain text, and that input could be as simple as hi, or it can be a password, or it can be a message. And what I want to do is I want to take that input, I want to feed it into some h of x function, and it's going to create a hash. And that hash is going to be a big list of alphanumeric characters, potentially hex-based numbers. So 0 to 9 and then A through F. And I want it to be the same size regardless of input, because again, it's kind of like a hash table where, you know, there's a certain size that it can be, and I can always add leading zeros to make it that size. And so why do I want to do this? Because I want to hide what my original message was. So that brings up the next part. One of the important things that makes a hash function secure is once we generate this hash, so let's say hi becomes that 523AFS2. And then let's say that Tim becomes 213AF12. And then let's say that car, or a full message, how about that? I do not like anime. That also becomes 11AF2B1. 2467. Okay, so they're all 7. Okay? And so to make this secure, I want to make sure that once I generate these hashed values, I cannot go back and figure out what the original input was. Because if I can, then why am I doing this? So that is called Preimage Resistance. I wanted to make sure I didn't get my terms confused. Let's see. Somebody said, Wikipedia, the term hash offers a natural analogy with its non-technical meaning to chop or make a mess out of something, given how hash functions scramble their input data to derive their output. Okay. Interesting. I thought it'd be somebody's last name or something. But yeah. And by the way, here's an example of a usage case of hashes and an example of not good usage of hashes. A good usage case is, suppose you're looking for somebody's information and you have something to map to. So for example, you have a name of a person and you want to get their phone number. So you feed that name to the hash function and it gives you an index where the phone number is stored. Or vice versa. You give the phone number and it gives you a spot where the name is stored. That's a good usage of a hash. A bad usage of hash is, for example, suppose you have everybody's birthday stored in the hash table and you want to print out all the people that have birthdays on January 5th. Well, hashes are not good for that because there's no easy way of accessing that. You'd have to search the entire thing and take n time, when if you had sorted it, it would be, you could potentially do it in log n time, or there'd be other ways of doing it better. So when you're trying to access patterns between data or groups of data within your data, hashes are not good for that. Hashes are only good for accessing data based on the given value that maps somewhere. So that's, I guess, an important thing. So don't just assume that hash tables are the best because we've done O of 1 time versus log n or n time or whatever. They're not. If you want to sort a list, hashing is not really going to help you at all. So hashing is only good for when you're storing data and you want to retrieve it quickly, but you're not trying to find patterns between the data. All right? Can you hash with month as index? You could. You could do that. And then you could find all the people that have January 5th. Yes. But then, what if I ask you then, okay, you have all the people stored in a hash table that hashes based on the date, so I can easily print out who's on January 5th. But then I ask you that for that same data, okay, give me everybody's last name. Then that hash table hash function is not going to help you out there. You have to remake an entire new hash table, an entire new hash function to be able to do that, which is hashing on the people's names, right? So it's not really going to help you unless you know ahead of time that very special case. So yeah, there's that. So anyways, I'm glad that actually came up because I was meaning to say that for a while actually, and then we kind of never touched it. So okay, so this is one of the cryptographic hash function properties that is important to have. Preimage resistance. By the way, somebody tell me how many viewers we have. I want to see how many people are still alive. Because I can't, I guess, I closed it to avoid lag. Okay, so the next thing, and I think this one should be relatively obvious, is quick computation. So, preimage resistance means 36 beers. All right, thanks. Cool. So it's low, but we started with 60 something, so we're at half there, but still okay. Still in the audience. That's nice. So, we don't want given a, or sorry, given h of a or h of x, we don't want someone to guess x, given that. So we don't want people to go backwards. However, the official definition of preimage resistance is, given h of a, it is infeasible to determine a. Infeasible. Not impossible. Infeasible. Why? Because it's impossible to make it impossible. To convert h of x, to convert x into h of x, or sorry, to feed x to our hash, to get h of x, you have to do something to it. Something. And that something had to be a computation. And you program that. Therefore, there's an answer to that. And this, given enough, and this is hacking, I suppose, given enough of these, and enough of these that you can run ahead of time. So if you can, even though you don't know what's in here, if you have the ability to feed it input and see what it comes out. So like, let's say, let me give you an example. So let's say that I feed it the numbers 5, 10, 8, 7, 22, and 32. And I feed it into this magic hash function. And it turns out that it gives me the following values back. Maybe, yeah, okay, sure, why not? It gives me 2, 5, 0, 8, 7, and 2. Okay? So brute force, no, that doesn't quite apply. We'll talk about brute force in a second. But, okay, given this, I know that this input mapped to h of x is going to give me, sorry, that one, 2. This one gives me 5. 10 gives me 0. 8 gives me 8. 7 gives me 7. 32 gives me 2. Can you tell me how I got from here to here? I'm going to assume you guys know. And that is, all this is happening here is I'm taking mod 10, or I'm taking the first digit, right? That's super obvious, super easy to crack. Okay, suppose that the way that I computed it was I multiply, I'm going to give another one. Suppose that I have these following numbers. I feed them into this box, and I get back from that 4, 6, and 10. What is that one? You guys tell me in chat. In the meantime, I'm going to see what somebody said. That's how MD5 was broken. Enough collisions gave enough info on how to hash values. Yes, so I was going to get to collisions in the next spot. So I'll get to collisions in a second. Frozen. X mod temp, and then x plus x divided by 10. You just need x mod 10. You don't need the division part. Unless you're doing integer division, in which case it is doing this almost the same thing. Yes, good job. Add digits. So yes, this hash function, all it's doing is it's adding the digits. And so that's very easy to know. However, here's the thing. Suppose that you're giving only 22 and you're giving 51. And you see 4 and 6. You may not see what is happening. Or here, actually better example. Let's go back to the integer one, to the first example. You feed it some value like 22 and you get 2. At that point, it could be anything. You don't know. You feed it some other value and you get a different number. But then notice how I feed it 22 and 32 and they gave me the same value. That's a collision. You know, we talked about collisions being a bad thing. So the best way to crack something is you find enough of these collisions and you start to see what specific values that you feed in give it a specific answer. So for example, if you see that always the 4th digit here is an A, whenever you're giving it something of maybe size 5 characters or size 3 characters, you start to see a pattern there. You start to see that little collision in the value. And given enough of these, you can reverse engineer that function. So then you say, okay, if I want pre-image resistance, what can I do to make it work? Well, I could make it completely random, because randomness is randomness, right? Well, not really, because in computers, there's no such thing as true randomness. Pseudo-random is what you use when you're using rand function or just about anything. There's no easy way to get a random number. In fact, some of the cool examples that I've seen is like, I don't know if it's LinkedIn or what company, is they have a lava lamp. And that lava lamp, the way they have it set up, it creates numbers. And they have a camera filming the lava lamp. And that camera has OCR so that it can convert the numbers that appear there into actual text, which is then fed into a list of random seeds to feed to pseudo-random number generators. And so because the seed changes every single time, then it's going to be random, and there's nature involved, because there's no easy way to generate a random number in a computer. Given enough values, you could crack how rand works in your programs. So whenever you use rand, in fact, it's quite easy. All you have to do is give it the same seed every time and feed in a bunch of values and see how they get mapped, and eventually you can figure it out. That's why when you run seed, you run it with a different input each time so that it creates a different set of numbers. But if you run seed with the same input, it'll always generate the same exact random number. So like seed 0 or seed 50, instead you use the seed to time, because the time is always changing, and that number is a number that started in like the 70s, the Linux number or whatever. And so basically, that's one way that we could make this really hard. But here's the thing. We also need to be quickly computable, right? Computing randomly is not as great. But okay, sure. Putting a camera and recording a lava lamp to tell us where to hash things could work. Well, yes, but then it brings up to the next requirement. It has to be deterministic. Now, what that means is every time that I give it a specific input, I want to always get the same output. With the lava lamp, it's not even considering the input. It's just looking at the number that is currently being displayed in the lava lamp, and that's where it's going to hash it to. That's useless, because next time that I feed it the same number, the lava lamp might be showing a completely different number. So while the lava lamp works good as a seed, it doesn't work good as an actual way to index things in the hash table. You always want, if you give it 22 and your algorithm is to add 2 plus 2, you always want whatever it is to always give you 4. You don't want tomorrow to feed it 22 and give you 5, because that's like trying to store data and now you can't retrieve it. Okay, questions. Tom Scott did a video on that company. Yeah, I probably saw that on YouTube too. When you make your SSH key, you need to move the mouse randomly so it grabs random numbers. Yeah, that's true. Yeah. So when you're making an SSH key for SSHing into like Sally or Bobby, and you don't want to use your password with a key, that key is a big randomly generated number, and it asks for input because it needs a seed. However, if you use the time that the computer's running at, people can guess when you made the account and just feed it different time stamps and see which one makes it. They can brute force it in that method. However, what they end up doing is they end up making your mouse move, because this is a random motion that I'm doing. And given this random motion, it uses the coordinates there as the input values to your seed. However, here's a good question for you. Suppose that somebody's job was to just make random numbers using their mouse. Do you think that if they were working there for a year and you fed all these into like a machine learning algorithm, do you think that we could predict the number that they're guessing? And I think that they could, because if you're working on this in a year, they're going to start a pattern. Maybe like, for example, me, I'm just going to be going in this direction, like left, right, with a little tilt. And it's always going to be that. And so maybe you can crack whether humans can make random things or not, right? Because they might be going in the same pattern every single time if you do it long enough. However, if it's a one-time thing, you try to move yourself random. But it's a nice little thing to kind of consider, right? It's kind of cool. So, yeah. Okay, so deterministic, the official definition of deterministic is that no matter how many times you parse a particular input to a hash function, you will always get the same result. And it's critical because if you got different hashes every single time, it would be impossible to keep track of the input. So between these three properties, to be deterministic, quick computation and preimage resistance, you can get your sort of initial, not so safe, but more safe than nothing, cryptographic hash function. So it has to be quickly computable. It doesn't matter if you have this amazing function that is super hard to get preimage resistance. It's deterministic because every time you feed it the same thing, it gets you the output, the same output. But then it takes like 10 days to compute it. So it's like you're trying to log into a page and it takes 10 days for it to open. Quite useless, right? So it has to be quickly computable. And that's not something to kind of quickly ignore. So for this next part, I'd rather show you the page. So let me pop that open. Looks like we're not going to get to tries today. See, tries, they just never come. I might just make a random video on that and make it optional. I'll probably do that. So I accidentally bump into my desk all the time, which moves my mouse. So yeah, I guess that could be some pseudo random thing. Is this the one? No, what is it? Cryptographic hash functions. Oh no, this is the one. No, it's not. Oh, this is not Geeks for Geeks. I lied. It's Block Geeks. That's what it is. How original. So I guess I didn't post this link. I should post it. Yeah. I'll post this on Canvas later. Have a small child bang. Could you create a pattern though of the child banging? Like, that's a real question. Are we pattern? There's a thing on Reddit the other day that said that they fed on 15,000 families patterns to try to predict whether somebody's going to get evicted or not, and they failed. But more than that showing that we are truly random, it's just showing we don't have enough data, to be honest, to be able to predict that. So yeah. Okay, what exactly is the purpose of cryptographic hash functions? The purpose of cryptographic hash functions is to have an input like this and to get an input like that. Maybe I can zoom in a little bit. And because this input you can store in a computer or in a server, and this one is your plaintext password. You may use your plaintext password in multiple websites, so you don't want people to store your plaintext password, because as we've seen over and over again, people get hacked, and when they get hacked, they see this. But this is peculiar to your specific system. Hackers can't use this password somewhere else because they're probably using a different hash function, or at least they should. More than likely, what ends up happening is when a company buys a security system, it comes with a hash function, but they have to give it the seed. So the seed is different for each customer, and the hash function is public. They just have no way of reversing it. And so even if the hash function is public, like MD5 was, what is not public is the seed value. And so that's why our friend here was saying that that's how they cracked MD5. Because here's the thing. The way that that you do this is as follows. So you have your inputs X. And I said that you feed it into this H of X, which then feeds it into your indices. And by indices, I mean what it really gives you is those chains of numbers and letters, and they're your hashed passwords, okay? But here's the thing. Me as a company or as an individual, I create this really amazing hash function, and I tell the world what it is. But that doesn't matter, because what it really has is it really has two inputs in here. It sort of becomes H of X comma Y. X are still your inputs that you're feeding, and it's still going to give you the hash values. However, the Y that's coming in is going to be your seed. And that's the number that you randomly generate, whether it be with a mouse, with a lava lamp, or you just ask somebody, yo, give me a random number, and then you don't tell them what it's for. I don't recommend you do that, though. Okay? So, given this method, so this is like 10, suppose that the way you do this is like X mod Y. I don't know, something like that. I forgot off the top of my head, RSA. But in your assignment, you're giving a specific seed number that I gave you. So just look at your assignment for that. You can't crack this. Or at least, hopefully you can't. And if you can't crack this, then you don't know what this is either. And so you give them this function that you say, oh yeah, that's what my function is doing. It's just doing X mod Y. And because you don't get what the original Y is, you cannot crack these X's. So what somebody, a hacker, will do is they will try to feed enough of these here to find a weakness in the system so that they can actually get the seed. So if I feed it 10 pesos to the machine and I get 10 hashes and I see that pattern, can I discover what this Y is? And it turns out with ND5, it took them a few years, but they did, and they cracked it. And by that, I can come up with a combination of different collisions that I can feed to this and figure out anybody's seed. And if I have somebody's seed, I have everybody's password at this point. Assuming that I hack into the system and steal the hashes, I can then reverse them with the seed and get the passwords. Or better yet, if I know somebody's hash, I can intercept that, because when you have your homie over here, it's connecting to Sally. What he sends here is the hash to Sally, and Sally has a hash stored. However, hacker intercepts his hash. Or sorry, no. Sorry. This is more complicated than that. But they send an encrypted message here. And then if you intercept that encrypted message, and you can from there get the hash value, because you can reverse it, then you can feed that hash value to Sally with a new encrypted message, and you have your man in the middle attacks, I believe. It's been a while. I learned this when I took blockchain class, actually. So here we have a couple of questions now. It could be maybe useful for signature on programs at companies, so you can't run the code unless you have the random signature in your program. Yeah, so certificates, that's called certificates, and it's a big deal in cybersecurity. At some point, I'm supposed to teach a cybersecurity and machine learning class, so I'll refresh all these things to be able to be more precise than just hand waving a lot of things here. But it's a whole field, and it's very, very cool, cybersecurity. So anyways, 5 more minutes. So as I said, this is what we're trying to do. We have our 3 properties that I was talking about. And so let's talk about this property 4, the Avalanche Effect. So you want, ideally, your hash function, to make it more secure, you don't want there to be patterns like I was saying. You want it so like if there's a tiny little modification in the input, as you see here, the only difference between these 2 lines is that the T is lowercase, to create completely different hashes. Why? Because if you create a hash function where modifying one character changes one character in your hashed value, that's how you start to see the pattern of what's happening there, and that's how you can crack the hash function or the seed or anything. You want it to be completely different. So that's called the Avalanche Effect. And it's a useful thing to have, but it's also tricky. And not just that, but this Avalanche Effect would be also useful in hashing in general to make sure that the big property of hashing is kept, which is things are uniformly distributed. And so if you get a bunch of values like 22, 32, 42, they all look really close. The only difference is one digit being different. You want them to hash to completely different spots. That uniform distribution is the Avalanche Effect. So not just for cybersecurity, but also just for general hashing, you do want very similar input to map to completely different spots to avoid clustering of data, which is a lot of collisions. And so finally, we got the 5th property, which is collision resistance. So what that is basically saying in plain text, I mean, you can read this on your own, is that given 2 people, and this is when the Bernoulli paradox is going to come in, given 2 values that you hash in, you want it to be infeasible, again, not impossible, but infeasible, because it's really hard to guarantee absolutes. You want it to be infeasible that the values are the same. So if you have 5 and 10 that you're hashing in, you don't want them both to hash at the same spot. So in other words, you don't want collisions. Why don't you want collisions? Because the more collisions you find, the easier it is to find the pattern and to crack the data. Because like, here's the thing. I have the password, and this is your assignment with RSA. I have the password, let me in. And somebody else has the password, I like cookies. and if they both hash to the same spot in the hash table, then technically I could write in my login, I could write I love cookies, and the other person could write let me in, and the computer will say that the password is correct when it's not. So is it likely that there are collisions in all the hash cryptographic hash functions? Yes, but most of them will make absolutely no sense and be really, really weird text. And it's very, very unlikely to have a combination of user password. But in theory, your Facebook password, you put in your email and you put in your password. In theory, there is probably another password that you could put into that machine and Facebook will accept it as valid password. And that will be a collision of the cryptographic hash function. Good luck trying to guess that though. You're probably going to get banned from servers for just trying to brute force and figure that out. But that's what a lot of people like to do to try to find these patterns, because the more collisions you find, the easier it is to see what the seed and the cryptographic hash function are made up of. And so that's kind of like the birthday paradox that I was saying. So the birthday paradox is, if you have in the room one person or two people, and you ask them when their birthday is, you know, the chances of another person having the same birthday are 0.27%, 1 over 365. Or 1 over 366 technically, because it's February, right? I guess. Although that's 1/4 less, so I don't know. But if you put in 23 people in there, then you have a 50-50 chance of 2 of them having the same birthday. And so the math behind that is here. So you can read that. Square root of 365, which is about 23, which means randomly chosen, 2 people have 50% chance. So what is the application in that? Well, suppose you're making a 128-bit hash, which means you hash a value and it creates 128 bits of just hash data. And so that means that you have 2 to the 128 power of possible values that you could get from your hash. So I guess if you're making a hash table to store this, it would be that size. But here's the thing. Using the birthday paradox, you have 50% chance to break the collision resistance, which means two things to hash to the same spot, if you feed it 2 to the 64th power of data. So it's much easier to find 2 things that collide than it is to break the preimage resistance. And so that's why it's typically what people do to break things such as MD5, which is to use to find the collisions, to find the pattern. Because whereas I can't figure out how to make a specific hash from the password it comes from. So if I have, this stuff is really tricky. So if I have the password let me in, and I feed it here, and I get some data here, which is like 1, 2, 3, and then I have hello, and I feed it in, I get 1, 2, 3. I've just cracked your password, even though they're not the same. It will be only useful in this website, not other websites, but it's still a security issue. However, trying to actually break out this pattern so that I can feed 1, 2, 3 and get back this, that's much, much harder to break. So usually when people try to crack security, they try to crack the bottom case, which is trying to crack a collision to log into a specific account. Then it would be to try to crack how to work it backwards. Is this the only way that passwords are created? Most cybersecurity is based on a form of hashing. So yes, I would say that's a soft yes, but a yes. However, you'd be surprised. There's a lot of dumb companies that keep passwords in plain text and then they get hacked and then those get published. And then you're like, are you kidding me? You didn't even hash it. You just kept it in a text file, literally in a text file, everybody's password. You'd be surprised. So there's a lot of jobs in cybersecurity. MGM announced that they were, they got hacked. And then like 2 days later, they announced they were hiring for cybersecurity jobs. And then they had fired like a quarter of their workforce. So RAM function is a hash function. It absolutely is a hash function. In fact, it's a really great example of a hash function. And your seed value is your seed value. So that's going to be the secure value that you put in. It 100% is a hash function. I'm not gonna talk about Merkle trees. I think that's as far as I'll get with that subject. If you want to learn more about cryptographic hashing or cybersecurity, Dr. Kim offers cybersecurity courses, and there's a cybersecurity master's that just got approved. As I said, I'm going to teach a machine learning and cybersecurity course. I will brush up on this stuff too before I teach it. But there's also a blockchain course, which the blockchain side, you know, whatever how we feel about that is how we feel about that. But the cool side of that is that he does talk a lot about this RSA, MD5 certificates, and all the cybersecurity stuff. Really cool stuff. It's I'll get back to you on the class numbers, but the blockchain course is like $789, which you can take with permission. And there was a bunch of undergraduates that took it. And then the cybersecurity ones that Dr. Kim teaches. CCS, no, because CS 448 and 449 are taught by Bergel, and those are not the ones that I'm talking about. They're part of the cybersecurity sort of specialist. You probably just need 326 and 370. You might not take it next semester, but the semester after that. But I don't know. Ask our homie that was talking about that here. I'll put the name on the chat. He knows, and he's on Discord as well. So yeah. Okay, so that concludes the lecture. I know we went a little bit beyond, but then again we had tech issues, so I think we stuck to the 115. I'm gonna make a separate video on tries. It's completely optional for you to see, maybe 10-20 minutes. I'm gonna actually do it immediately after this. I'm not gonna stream it, so I don't force you guys to see it. But it's an optional topic, but I thought, why not make a video on it? But for now, that's the end of lecture, so thank you for staying. You can leave now if you have other things to do. You could have left before, technically. But now I'm going to open it up for questions. In fact, I'm going to pop open the assignment as well. Yeah, restarted the live stream and it hit like 12:13. Yeah, so actually, yeah, I think we're right on spot. We're about 4 minutes off. So yeah, ask me homework questions. Otherwise, I can just talk about the homework, actually. I can introduce you to the homework. Yeah, let's do that, since I technically have like 2 minutes left according to that. And then you can ask me questions of the homework, or you can just go. So I think this is the first time that I use an assignment that I had done before. I did this assignment for a different 302 class. So there's possibility that there's a similar version out there somewhere. Just don't look for it though. But if there is, send it to me so that I can take it down. So yes. But the reason why is because I really like the assignment, and I never actually given it myself in my class. Even though I made the assignment, I made it for a different instructor. So I was like, I'm going to use it this time for my class. So let me download it actually, look here. Hold on a second. Can you see? Yeah, you can see that. Perfect. Okay, let me pop it open in PDF format. And just start writing questions in general for the lecture. I'll answer your questions as they come. All right. So here we have 2 questions already. For question 1 in the worksheet, are we supposed to find 4 individual formulas for an Alyx grandchild? Yes. So 4 individual formulas. I did that in the lecture, literally. So you can check that out if you're really, really stuck. And oh yeah, somebody else answered the question already. Nice. Yeah, I'm glad you guys are helping each other. Okay, so you guys can see that pretty clearly, I think, right? Actually, maybe I can go in a little closer. Okay, so I don't want to just read from it. You could read it on your own. So I think the first thing that I want to talk about is here's your hash function. That should be very easy to implement if you know how modulus works, I suppose. And let's talk about the hashing password. Again, we don't want to store in plain text because we don't want to be hacked and then just leak everybody's password. And so we're going to be making that hash function to encrypt the password. And we're going to use the simplified version of the Rsa algorithm. Rsa, Google that. Tons of talk about that. Take Kim's class. He'll test you on that even. And so the way that the Rsa algorithm works is m to the power of e mod n. And so I go ahead and explain what each value is. So m is a numerical representation of the password. So you got to take your password, which is usually in text, sometimes special characters as well, and you got to convert that into numbers. And the easiest way to do that is just to use the ASCII conversion table. So like A is 90 or something. I don't know. It's just a number. It doesn't matter how you do it. You just have to. This isn't secure at all. People can reverse engineer in this part, so you don't worry about it. You just make it simple, make it into a number. Obviously, make them unique though. Don't make 2 characters in your password to be the same number. That's bad. That decreases security. Make them all be unique. So if you have 26 letters, lowercase and uppercase, including special symbols or whatever, let's say you got about 60 characters that you can put in there. Numbers, maybe 70 total. You want them each to be unique. You don't want A and I or uppercase A and lowercase a to be the same. That's why they say your passwords are uppercase and lowercase are different. Some websites I've seen, like government websites actually, where like all passwords are lower. I think USPS used to be like this. Like, or no, was it USPS? Or no, the DMV. Yeah, the DMV. The DMV doesn't care if your password is uppercase or lowercase. It's the same. It's the same password. And that's because their conversion here that they're using, they were like, yeah, no, we're just going to convert uppercase and lowercase into the same value, numerical representation. It's not bad. It's just the smaller the amount of possible passwords there are, you can use brute force to just try them all until you figure out the user's password. So if you know that most people will probably not put a password that's bigger than 8 characters, you know, each character, let's say there's 50 characters each. That's 50 times 50 times 50 times 50. So 50 to the 8th power are the possible combinations you could have to do to brute force. But then you can get a dictionary attack. So because you know most people are going to be using not just random letters, but meaningful letters, like, or random words, meaningful words. So they might use like English words in there rather than just randomness. So then your dictionary goes down from 50 to the 8th to maybe 50 to the 4th. So now the number of brute force attempts you have to do is much, much smaller than the possible combinations, because you know people are not going to put random characters. They're going to put mnemonic things or things that make sense, words, birthdays, that sort of format. So, yeah. Cool, makes sense. Imagine really it could be a way for this function 1, 2, 3 m value is 3, 2, 1. I don't know what the last thing you said means. Or did I say 1, 2, 3 before? I don't know what you're talking about with 1, 2, 3s. So clear out on that. You're adding the ASCII values. Oh yeah. Yes. So yes, already there's a problem, right? And I think I make a point of that in the assignment. So you don't want to just necessarily add them together because you can have combinations. So one of the things that you can do is you can use exponents for each one. So like the first number is going to be squared, the second one squared, and then cubed into the 4th. So that way they're different. So like if you have the words A, B, C, and B, C, A, let's say that A gets converted to 1, 2, 1, 3, and this is 3, 2, 1. So you can do like 1 squared plus 2 squared plus 3 squared. And this one is 3 squared plus 2 squared plus 1 squared. But then you're like, it can be flipped around. So then you can change this exponent based on the location that it's at. So you can do like that. So now they're different. See that? And it's not going to eliminate all possible cases, but you can do a specific operation based on the location of the digit. So you add that into the randomness. There still might be collisions. I can guarantee you in that case there might be, like, especially if you said like AAA or something. But it fixes it. But yes, it's a little bit tricky. Oh, snap. Sorry. You're right. I was writing this. My apologies. So I had 1, 2, 3 and 3, 2, 1. And then I go ahead and do a specific operation on each digit based on the location that it's at, such as like squaring the digit. That way, the order matters for what operation I apply on the digit. And that helps a little bit with that case. So that's what I was trying to say. Okay. So that's what your M is. N is the product of 2 prime numbers that you pick. And usually you want to pick really big prime numbers. So in this case, we picked P and Q to be those 2 prime numbers. And those are indeed prime numbers. And so you want to multiply them together and you want to create your n. This you randomly generate, but you want them to be prime numbers ideally. So usually you just pick really big prime numbers for that. But you could pick potentially anything that you want. What you don't want though is you don't want them to not be prime numbers, because then it decreases the security of your system. So that's why we picked that for that. Okay, what is E? E has to be a number between 1 and the totient of P and Q. So what is the totient of P and Q? The totient of P and Q is going to be P minus 1 and Q minus 1 multiplied together, which is this value. So E has to be somewhere between this. It also has to be co-prime with the totient. So they must not share a factor of other than 1 between your E and this value. So we could pick a really big number, but that's going to make your computations painful. So I went ahead and picked a small number. So what that really means is you have your P and Q multiplied together, and then you have your P and Q multiplied together, but you subtract 1 from each before you do the multiplication. And so that's the one that you're going to pick. You're going to pick a number between them, but you don't want it to share a factor other than 1. So the easiest thing to do is just to pick a prime number, but you could pick just about anything that didn't share a factor there. So ultimately, you end up with this guy. And what makes this secure is this number primarily. But also this number has to do with it. And so when you do this, because of this modulus, you're not going to get any number bigger than that. You can get anything smaller than that, but not bigger, right? So our password can be stored as any number between this and this. And so if you want to store this in your actual array, you could make an array this big, but we're just going to make an array size 23 and then use modulus 23 on this to be able to hash it in there. So really, you're doing 2 hashings in this assignment. You're doing a hashing to generate the password as a hash, and then you're hashing that password into this table with mod23 just to insert the password user combination. So your input, if I scroll down, where's my mouse? Here we go. Is going to look like this. User and password, user and password, user and password. And the way it's going to get stored is like this. So for example, this one probably matches one of those 3 passwords. Here's the other 2, because you saw there was 3 users. And the way it's getting hashed is based on mod 23 of that. And so when you search, so this is like trying to log in. What does, oh, search or delete. I think this S means to search, D means to search and then delete. So you try to go in there. This value, the new password, is going to be hashed. And then after it's hashed, it's going to take the mod23 and it's going to look there and see if it's there. And if it is there, it logs you in. If it's not, then it does not log you in. My outputs and yours should match if you feeded this input file and the search file. If you don't, then of course it's not going to match. Mine's just, I just gave you a test file, but I recommend you test it yourself. Questions? Oh well, that was the question. So the hash password should match as long as you pick the same value here. Come on. If you pick the same totient of P and you pick the same prime numbers, so you get the same thing here. If you get the same here, G of M, then yes, your values will match. If you pick something different, then they wouldn't match. So I recommend that you just pick that to the assignment. But then after that, you can explore and try different values afterwards. But yes, this is my company decided we're gonna use this number and this number. Your company could have used a different number. And in this case, this you want to keep secret. Nope, you don't do anything to the username. You know, wanted to make it more secure, I could do that. But I decided that if we get hacked, we're going to release everybody's username, but at least we won't release their passwords. Yeah, you do get a bunch of, so I do give you a bunch of code, so you have the, if you follow my skeleton code, then it should be a relatively easy assignment. Come say hi. Dog. She's been chilling there all lecture. Good dog. You want to right click on the file and then save it. And then if you're not opening it in Linux, then you might not show, it might not show as data, but it should. It's you need to add a .txt at the end, or if you're opening it on Linux, open it as, and it should be a text file. You can use cat. Why do I use fmod? That's a good question. When I created this assignment, I found out that using modulus can be quite an expensive operation. And if you just use regular mod, things overflow and crash and explode. So fmod is the only way that I could get it working and not take like 10 days to run. So there's that collision resistance right there and all that. But remember, you want that computation, quick computation. And if you don't use fmod, no quick computation. Try fiddling with it. Try using just normal mod. And then just sit back and enjoy watching it, try to figure out what's happening. What stream did you go over question 1? Well, what's question 1 again? I forgot. I think I don't know, probably. What was question 1? I don't know. I gotta pop it open now. Question 1? Are you kidding me? Oh wait, this is not the right worksheet. I was about to say. Probably when I was talking about AVLs, I think, but any of the 3 lectures potentially. If you change it to text, do you have to add text to the with a.out? Well, yes, you would, but just do Linux, and with Linux you use the cat command, and you don't have to change the .txt. In fact, you don't need to add an extension to any file. You can right-click that file, open with a specific program. In Windows, Notepad++, in Linux, gedit, in Mac, I don't know, cat as well. I don't know, whatever Mac uses. And then the file extension is only an assistant to your OS to know how to open, which program to use to open the file. But you don't change the file itself. So if you manually open it with a program, you don't need to know that input file. You need to know the file extension for it, as long as you know what it is. Regular Notepad and Windows will not work because the file itself was created in Linux, which uses different line feeds for it. There's a thing called carriage return and line feed, and in Linux we always talk about line feed with end line or whatever. But if I remember correctly, there's LF, which is a line feed, and then there's carriage return, which I don't know, it's like RE or something, I don't know. And so in Linux, all it uses is line feed. In Windows, I think it uses both, and Mac only uses return. And so if you want to be super compatible, you put both at each line. If not, then what ends up happening in Windows is, if you only use line feed in Windows, and Linux looks nice, file. In Windows, it's just one long line of code or text. Carriage return. Thank you, CR. Let's see. Why does stream keep looping? That's scary. Are we really looping? I don't know. Maybe we're stuck in assignments 9s. Live, die, repeat. Okay. Alright then. If there are no more questions, then that's the end of the lecture. So, questions? Hit me up with those questions. Edge of tomorrow. I'm just waiting for questions. Padme. Where can I send you money to fix the internet? You know, I wish it was question about money, but I'm paying like $100, almost $50 to Cox for Gigablast, and I have like third world country. No, you know what? That's a lie. In Mexico, I have Fiverr. I have way faster and better internet than here. So, yeah, no, this is just, it's a shame for Cox. But yeah, my upload speed is like 20 megabits per second, and my download is actually 35. Sorry, other way around, which is ridiculous for the download. And the packet loss was killing me, because the upload is okay. I can live with the upload. That's as long as the upload is good, the download can be bad. But unfortunately, the packet loss is killing me. So on the test, would we get a minimal point reduction, like you said, if we were to use a bigger hash table? Yes, you get a minimal point reduction. Is the test going to be made harder because it's open notes? Absolutely. Absolutely, yes, it will be harder. Because I can't just ask you like copy-paste questions where you can just Google and copy-paste. I have to ask you questions where you have to like actually understand the question. Like conceptual questions. Because even an ABL should be easy, because like you have your notes, you even have your program to verify your answers. Are you gonna start to stream games too? No, probably not. Not with this kind of internet, I'm not. Other questions? She wants to sleep. I think I'll just let her go to sleep. She just literally sits in the back of my chair all the time. So. All right. Thank you guys for coming then. I guess there are no more questions. So that is it. Do you know how the SU grading is going to work? Nothing yet. No news on that yet. We just have to wait and see what the people on the top say. The top men say about that. Top men and women technically, but the old quote is top men. You know, from Indiana Jones. At the end of the movie, he's like, top men are working on this. Top men. I will make a video on Trice individually and upload it to my channel, so you can check that out later. It's completely optional. Maybe extra credit. Who knows? All right. Stay safe. Don't get COVID-19. Wash your hands. Do all that kind of stuff. And then I'll see you guys on Thursday, 12 p.m. Assuming the internet gods let me. All right. See ya.